convinced you that all we have to do in order to derive thermodynamics is to compute this number of microstate, which corresponds to a particular macrostate which is specified by these variables. Okay, the number of particles, the volume, and the energy. Okay, and now what I want to do is to derive, compute this number for the ideal gas. For ideal classical, well, let's say ideal gas, okay? Because we are going to use quantum mechanics to count the states. Okay, so ideal gas means the particles are not interacting, and this is an approximation. So there are several reasons why this is an important, why we discuss about ideal gases, which do not exist in reality. One reason is that this is like a prototype system which helps us understanding how we do these calculations. Okay? There is a simple system for which we can understand what is the nature of the calculation which brings us from this number to thermodynamics. Then, of course, for more complicated systems, when we have real gases or when we have more realistic systems, the calculation will be more complicated, will be more difficult. But the idea will be the same. Okay? So it's good to have a simple system for which we can understand what is the procedure. Okay? Then the other thing is that real gases actually behave in the way we are going to behave as ideal gases for large temperatures, at large temperatures. So this is also an exercise which gives also some quantitative answers. And then of course this is a reference, if you want, is a reference system in terms of which you can understand the effects, for example, of interaction between the particles or of quantum effects. Okay, so it's good to have to do this exercise and to have this in mind. Okay, so as we said on Monday, it is simple to see that well, we expect already that this omega is proportional to v to the n, and this is because essentially here what we have to do in order to compute this number is to compute the number of ways in which you can have n particles in a volume V have energy E. Okay? And well, already by distributing the particles in the volume, we figure out that if the particles are distinguishable, then each particle can be, if we divide the volume in small elements of size V, then each particle can be distributed in big V divided by small v number of ways, and this is the total number of ways in which we can divide the system, okay? In which we can distribute the particles. And already this tells us that the derivative of the log of omega with respect to v, if we keep n and energy constant, must be equal to n divided by v. And this gives us the we know that this is P divided by T, and so this gives us the ideal gas law. Okay. now we want to be more specific and really compute this number. In order to do this, we have to be more specific about our particles. So now our particles are going to be particles inside a box of volume V. And let's assume that we want to describe them in terms of quantum mechanics. So each particle will be described by its wave function. And what are the wave functions of free particles in a box? Plane waves, okay? So this wave function is going to be something like this, where this wave vector here, yes, is related to the momentum and can only take values. I mean, I have to impose boundary conditions on this problem, and then the k is going to be a three-dimensional vector, and each of the coordinates must be of the form 2 pi over L times an integer. Well, this A is equal to x, y, or z, and this integer n can be any integer, so 0, plus minus 1, plus minus 2, etc. Okay. And what is the energy of this particle? The energy of this particle depends on the k, and sorry? Yes, is h bar square k squared over 2m, right? It's momentum squared divided by 2m. It's just the kinetic energy. Okay? And okay, now if I write it in terms of these numbers n, so this will be h squared without, this is not h bar, I mean h bar is h divided by 2 pi, but if I multiply by 2 pi I get h, n squared divided by 2m L squared. Well, here L is the length, is the size of the box, okay? So L is V to the 1/3, okay? I have a cubic box. And this n squared is nx squared plus ny squared plus nz squared. Okay? Now, if I want to compute the total energy, so a configuration, a microstate of my system will be specified by these three numbers for each particle, or these three numbers for each particle. Okay? So the microstate corresponds to 3n integers numbers, which are, say, nx of particle r, well, NAR, where A is equal to 1 or X, Y, and Z, and R is equal, goes from 1 to N. Okay? And let me call, let me just use one index in order to be, so let me rename this as just a vector NA, where this index A goes from 1 to 3n. Okay? So I have to specify for each of the particle these 3 integers, so I have 3n integers. Okay? And in terms of these 3n integers, my total energy will be just the sum of these energies over all the particles, right? So it will be the sum of this term over all the values of A. So it will be just h squared 2m, well, this is the volume to the 2/3, times the sum on all A of NA squared. And A goes from 1 to 3n. Right? This is the energy. So now let's think about this problem geometrically. So if you think now I write a 3n dimensional space of this vector n. Okay? Of this vector n here, with 3n components. It's a very high dimensional space. Okay? So what I'm interested in, so this is the radius, for a point n, if you have a point n here, then all the points which have energy E are all those which are at the same distance from the origin. Okay, so they are all those which are on the same on the surface of the same sphere. Okay, so they are all those which are also on the surface of a sphere whose radius, the radius of the sphere is the square root of 2m v to the 2/3 divided by times E divided by h squared. Okay? So you see, I have to deal with a geometrical problem, which is that of computing. So if I want to compute the number of states, the number of assignment of the number of states which have the same energy, I mean, this number is equal to the number of points on this surface. Okay? Now, so you should think that here there are, say, discrete points, right? Okay. So this is an integer lattice, if you want, 3-dimensional integer lattice. So, however, it is better to it is preferable to deal with continuous variables. Okay, so So, so the first thing is, in principle, I have to compute the number of points which are exactly on this surface. But essentially, what I can do is to essentially compute the number of points which are inside the whole sphere. Okay, and let this number, so the number of points in the sphere, if this is V of E, then the number of points on the surface will be related to the derivative of the volume with respect to E. No? I mean, if I change the energy, then if I increase the energy, then this sphere will get a bit larger. Okay. Okay. So the number of points will be essentially related to how this volume, to the derivative of this volume with respect to the energy. Okay. Okay, so let us compute. I want to compute this volume here, the number of points which are inside here. So let me do it in two steps. First, I want to transform this from a discrete problem into a continuous problem, and then we have to compute the volume of a sphere in 3n dimensions. Okay. So the first step is simple. And so, I mean, if you what our volume of E is equal to the sum on all the vectors n, such that n, the modulus squared of n is less than r squared of 1. Okay, so for each point inside the sphere, so such that n squared is less than r squared, I have to count one state. Okay, and this will give me the total number of states with energy less than E. Okay, now this sum, I want to, so this sum is the sum of over n1 and 2 up to n of 3n. Right? So I want to change this sum of n of NA from minus infinity to infinity into an integral. Okay, and the way I want to do this is to change this into an integral over k, and from minus infinity to infinity. And since k is 2 pi L times n. Okay, so you see, since L, the size of the box is macroscopic, is very large. When n changes, so this is essentially a continuous variable. Okay, so the sum over n can be well approximated by an integral in decay, and the coefficient here must be such that, of course, the dn here is 1. So the dk here is L divided by 2 pi. Okay? So this is a general formula you might have already seen, where you turn sums of occupation number, sums over integers into sums over momenta. Okay, so if I do this, then what I have here, I have 3n of these integrals. So I have an integral over a 3n dimensional vector k. I have factor 2 pi to the 3n, and I have a L to the 3n, which is just the volume to the n. Okay, and what I have to do is to do this integral on all values of k squared, such that the radius is less than some k0 squared, where this k0 must be equal to 2 pi over L times that object there, which is 2m v to the 2/3 times e over h squared. Okay, and so this the radius of this sphere will be well, this L is just v to the 1/3, so these two things cancel. So it's just 2 pi over h 2m. Okay. So this is essentially v to the n over 2 pi to the 3n. And what I have here is essentially the volume of the sphere. Let me call it differently. The volume of a sphere of radius k0. Okay. Okay, so let me write this k0 here. Yes? Is it okay?
Yeah, I think the unit of r is length, right?
Yeah?
Okay, and the unit of k is 1 over length, right?
Yes.
Then now, okay, here.
Okay, you want to check whether. So okay, yeah. So these.
When we calculate k0.
Okay, so let's check. You want to check the units of this. Okay. So this is. So let's see. This energy times mass divided by h. So
I think it's easy. Yeah. The square thing is just a unit of length because it's r.
sorry. Now let's compute these units. Okay, so this is so h is length times momentum, which is length times momentum, which is mass times length squared times divided by time, right? And so this is mass times energy. So energy is, say, for example, momentum squared, so is length squared divided by t squared divided by mass. And so this is length squared divided by see, the m cancels. So the dimension of this would be L squared m divided by t, and here there is square root of L squared divided by T. So, no, sorry. I have 1 over H, so it's T L squared. There is a mass which is the square root of L squared divided by T squared. So this is 1 over L times a mass. So am I missing something? The dimension of H is this, right? No. So the M should be up here, right? This is the unit of energy. Okay? This is the unit of energy. So the M should be, there should be an M squared here. Okay? And then this is 1 over L. Okay? Okay. Okay, so no, but it's good to check units to be sure that. Okay, so now we have to do this bit of math, which is the volume, computing the volume V of R, let's call it Vn of R, of the n-dimensional sphere, okay, of radius R, okay. Okay. First of all, we do this calculation by saying that, so if you, in this V, Vn of R will be an integral, like this, will be an integral in dn x, where, say, x squared is less than R squared, okay? Now, I can change variables here and change, call x prime equal to R times x. So this will become R to the n times the integral on the unit sphere times the volume of the sphere of radius 1. Okay? So we only need to compute the volume of the sphere of radius 1. Yeah? Question? Of the unit sphere. And by the way, if we want to compute the surface of the sphere, then you can argue that this thing will be n times R to the n minus 1 times the Vn of 1 times dr. So you see, this is the surface of the sphere of radius r in n dimensions. Okay. Very good. So the problem now is to compute this Vn of 1. So the idea, in order to compute this object here, is to start from an apparently different object. R to the n times this. But I did a change of variables. So you take any you change any variable x on which you are integrating here into a variable x a prime, which is x a divided by r. Okay. So if you do this, of course, the dx is r times dx prime, and you have a factor r for each of the dx. So you have r to the n. And what you are left is just the same integral with r replaced by 1, which is the volume of the unit sphere. Okay? Very good. So we compute these things by the following observation. So the first thing is, let's compute this integral I, which is the integral from minus infinity to infinity in dx e to the minus x squared. So this looks like a completely unrelated problem, but it's useful. Okay. So in order to compute this integral, this is an integral which is not easy to, not straightforward to integrate. But there is a trick you can use, which is instead of computing I, compute I squared. So I squared is clearly the integral from minus infinity to infinity of dx e to the minus x squared times another integral of this type, which I can call integral on dy e to the minus y squared. Now you see I have an integral on x and y, and I can transform to polar coordinates. And the nice thing is that what I'm integrating is e to the minus x squared minus y squared, which is just the radius square. It depends only on the radial coordinate. Okay? Then this integral is just 2 pi, which is the integral on the angle, okay, times the integral from 0 to infinity in dr r e to the minus r squared. Okay? When I transform to polar coordinates, so this is the integrand is just e to the minus r squared, and then I have dx dy, which is just the d theta dr times r, and I can integrate over theta from 0 to 2 pi, and gives me 2 pi. Okay? And now you see that I have 2 r dr is just the differential of r squared. So if I make another change of variable and call z is equal to r squared, then this is just the integral from 0 to infinity of pi times dz e to the minus z. And this integral now is very easy to do. Okay? And it's just one. The integral of is just e to the minus z computed in 0 and computed minus computed in infinity is just 1. So this is pi. Okay? So what we have found is that this integral is square root of pi. So I squared is equal to pi, so this integral is equal to square root of pi. Very good. Now we can do the same thing, but instead compute I to the power n. Okay? And I to the power n, well, we know already that is going to be pi to the n over 2. But we can also compute it using the same trick. Okay? And we know that, so it will be the integral dx1 dxn of e to the minus x1 squared minus x2 squared minus xn squared all the integrals from minus infinity to infinity. And again, what I'm integrating only, I can change variables to radial coordinates, to spherical coordinates in n dimension. And what I'm integrating only depends on the radius. And so what I have here is that I have the integral on the solid angle in n dimension, which will give me the sphere of the unit, the surface of the unit sphere. Okay, and then I have an integral. So I have the surface of the unit sphere, which is just n times v1, vn of 1. Times an integral from 0 to infinity dr r to the n minus 1 e to the minus r squared. Okay? Very good. So, and now we can compute this integral in the same manner as we did before. I mean, we will again change variables in if we call z is equal to r squared, and you change variable, then you get that this in is equal to n vn of 1. Now, of course, r is equal to square root z, and the dz is 1 over, so the dz is, dr is dz over 2 square root z, right? So I have a 1/2 which comes from the from this, and then I have dz over square root z, and then z to the n over 2 minus 1, n minus 1 over 2, and e to the minus z. Okay, so this is n over 2 vn of 1 times an object, which is an integral from minus infinity to infinity z, z to the n over 2 minus 1, e to the minus z. This object is called the gamma function of n over 2. Have you seen it? You have seen it? Should we, so can I assume that you know what it is? Okay. Very good. So, so this is n over 2, gamma n over 2 times v n of 1. And n over 2 times gamma of n over 2 is what? So it's gamma of n over 2 plus 1, which is n over 2 factorial. Okay? So the result is that this integral, I to the power n is n over 2 factorial times the volume of the unit sphere. But this is also equal to square root pi over n, so that this tells me that the volume of the unit sphere is equal to pi to the n over 2 divided by n over 2 factorial. Oh, that's nice. So let's check that this works. So for n equal to 1, n equal to 1 means that we have just one dimension. The sphere of radius 1 should be 2, because it's just a segment from -1 to 1. The volume is 2. And you have, so in n equal to 1, you have square root pi divided by 1/2 factorial is essentially the gamma of 3/2. Sorry? And the gamma of 3/2 is 1/2. The gamma of 1/2. The gamma of 1/2 is square root 2 pi, because it's essentially equal to this. This, I mean, if you change variables, this is the gamma of 1/2. So this is square root pi. So you get, in one dimension you get 2. Okay. In 2 dimension is even simpler, because you get just pi. Pi divided by 1 factorial, which is 1. Okay, it's pi. 3 dimension, you can check, you get what it should be. Okay. Very good. So now, now that we have this thing, we can compute our volume. Well, the other thing that we need is an estimate of what is n factorial for large n. Yes, so you know Stirling approximation, okay? Okay, so I don't need to. So you know that Stirling's formula, that n factorial is essentially n to the n e to the minus n times, square root 2 pi n 1 plus, etc., etc., okay? So what we need is just this. This you know. If you don't know, I mean, I will convince you that it is like this. I mean, it just takes two minutes. Right? So let's try to compute log n factorial. So n factorial is n times n minus 1 times n minus 2, etc., etc. Okay, so and the log of the product is the sum of the terms. Okay, so this is the sum on I equal to 1 to n of the log of I. All the integers from 1 to n. You sum, okay. So now this is x. So if you plot the log of x, is log x. Okay, what is this integral? Well, this integral, you take the integers 1, 2, 3, 4, 5, 6, 7, etc. And then you do this. You do this construction, and this integral is the area under is this area under these rectangles, okay? Now this is clearly less than the integral from 1 to n of log x, okay? This is clearly less than the integral from 1 to n dx of log x, okay? So from this we get that log n factorial is less than, and this integral you do is n log n, sorry, I call it small n, n log n minus n. This is when you compute it up here, and then when you compute it down here, there is a plus 1. There is a plus 1. Very good. So the other thing you can do is to take the function which is log of x minus 1. Log x minus 1 will pass through this other point. This is log, this function here is log x minus 1. Okay? And then this will be larger than, I mean, the area under these rectangles will be larger than the area, the integral from, well, in this case, from 2 to n, from 2 to n dx of log of x minus 1. Okay? But this is equal to the integral from 1 to n minus 1 of dx log x. You just change x into x minus 1, or x minus 1 into x. And this is equal to n minus 1 log n minus 1 minus n plus 1 plus 1. Okay? Okay, so you have that we have found this formula that minus n plus 2. Okay. Now, if you take so now if you divide log n, so this implies that if you take log n factorial and divided by n log n minus n, this is less than something which is 1 plus 1 divided by n log n minus n, and less than something which is, oh sorry, this is always n, small n. Something which is again n minus 1 log n minus 1 minus n plus 2 divided by n log n minus n. Now if you take the limit as n goes to infinity, this goes to 1 and this also goes to 1. When n goes to infinity, I mean the leading term is always n log n minus n, which is the same as this. So this shows that when n is very, very large, this is essentially 1. So log n factorial is essentially n log n minus n. Okay? Okay, so we take for granted that we can approximate, like, I mean, in our case, n will be 10 to the 23, so we are very close to the limit n going to infinity. So it's very safe to take this approximation. Okay. Okay, let's go back to our original problem, because now we have all the elements. Okay, so now the volume, this volume, which is related to the number of configuration I want to compute, is this B, is equal to B to the n 2 pi to the 3n times pi to the 3n over 2, and then I have E, well, I have n to the, sorry, E to the 3 over 2n log 3 over 2n minus 3 over 2n with the minus sign, because it's in the denominator. And then I have k0 to the power n, which is 2 pi to the power 3n over h to the power 3n times 2m e to the power 3n over 2. Okay. Now, what I'm interested in is essentially the log of this. And in particular, I'm interested in the part of the log of omega which increases, which is proportional to n. Okay, so you see, if I take the derivative of this with respect to the energy, will essentially be proportional to 3n divided by E of this object. Okay, but this factor, when I take the log, is just a factor which does not depend on n. So that essentially for all this calculation I can really substitute the volume, I mean the surface with the volume. This is just because when you take the derivative, you will find that the derivative of this volume with respect to the energy is equal to 3n over 2e times the volume itself. Okay. When I take the log, I will have the log of this plus the log of this. But the log of this is just a constant, whereas the log of this is proportional to n. Okay, so to all practical purposes, I can just assume that this omega is given by the volume. Okay. And now, well, you just do a little bit of algebra, and so if you take, so the entropy will be k times the log of this volume, of this expression here, and so there are so So you see, there are some factors which cancel. So for example, this and this, and there is everything is okay. So let me just write the final result. Because I want to discuss some consequences. So if you do the calculation, you will get that this is 3n over 2 times k times the log of 4 pi m e v to the 2/3 over 3n h squared plus 1. Okay. So this is so this is the final result. And now from this we can compute all of thermodynamics. So let us check. So, yeah. So, if you want, okay. So, for example, you see the dependence on the volume is of the order n times k times log v. So this tells you that if you take the derivative of the s with respect to the volume constant n and e, this tells you this is equal to nk divided by v. And this must be equal to the pressure divided by temperature, so you get the gas law, the ideal gas law. The other thing is let's compute the temperature. So you know that the derivative of S with respect to the energy at constant N and V, this must be equal to 1 over the temperature. And so if you do this, you get 3n over 2 times k. And then the only term which contributes is the logarithm of the energy. Because all the other terms are just, just constant. And so you get times 1 over the energy. And this implies that the energy is equal to 3n over 2 kT. So the energy of an ideal gas is independent of volume. So only depends on the temperature. So at constant temperature, if you do transformation at constant temperature, the energy, internal energy of the gas will not change. Okay. So you can also, so for example, from this, you can compute the specific heat at constant volume. The specific heat at constant volume implies doing a transformation where you keep constant the volume. Then you don't perform any work on the system. Then the heat which is absorbed is just the change in the internal energy. Okay, so it's just dE dt at constant n and v, and from this is just 3n k over 2. Okay, so the specific heat is at constant volume is a constant. You can also think of computing, let's compute the specific heat at constant pressure. If you want to compute the specific heat at constant pressure, then you have to consider that the heat which is absorbed when you change temperature comes also from the fact that if the pressure is constant, the volume will change. And then there will be some work done on the system. Okay? And since you know that, so the heat will be the change in the energy minus the work done on the system. Okay? And and this is the differential at constant pressure. Is the differential of E plus PV. But PV is just NKT, and this is 3/2 NKT. So this is just the differential of 5/2 NKT. So this is just 5/2 NK times dt. Okay. So if you the specific heat at constant pressure is just 5 NK over 2. Okay. So from which, you recover the fact that the ratio between these two is 5/3. Now the other thing, you can instead study adiabatic transformations. In adiabatic transformation, you see that the entropy depends on the energy through this combination, energy times volume to the 2/3. And this is something which is quite general, actually. I mean, so the fact that the entropy does not depend for an ideal gas, quantum or classical, depends on the volume and on the energy only through the combination. So this is only a function, we call it sigma of n and E times V to the 2/3. This implies that when you do an adiabatic transformation, the entropy is constant, and then E times V must be a constant. EV to the 2/3 constant in adiabatic transformation. Now the energy is this, but you can also write it as 3/2 times PV. So that if you substitute this, you see that P times V to the 5/3 is constant in adiabatic transformation. So isothermal transformation, when T is constant, PV is constant. So this is the law which will give you the adiabatic transformation, isothermal transformation. Whereas adiabatic transformation will have a different law, which is P, where P times the volume to the power 5/3 is equal to a constant. And yes. So let me also remind that, so if you compute, I mean, if you have this relation here, then then this implies that the so this implies the relation that energy should be equal to 2/3 3/2 times PV. And why is this? Because the pressure, well, you can write the pressure from thermodynamics as minus the derivative of the energy with respect to the volume at constant n and t. Now, if, sorry, n s, because yeah, you can invert this relation for the energy. And so if you invert this relation for the energy, you see that the energy would be V to the minus 2/3 times a function which only depends on n. And so since when you keep S constant, the energy is V to the minus 3/3, this gives you that directly that this is this derivative is 2/3 times the energy divided by V. And then this relation gives you this. Okay, this is an equation which is more general than this one because it will hold also for quantum gases, not only for classical gases. Okay, so questions? So, looks like you can get everything, everything is fine, but actually there is a problem. There is a problem with this formula and with this derivation. And the problem is that if you look, you would like that the entropy to have the property that if you consider a system which is A times bigger in a volume which is A times larger and with an energy which is A times larger, then you should get an entropy which is also A times larger. Right? So this is extensivity. Extensivity means that if you take your system, and if you take a system which is A times bigger, so which has A times more particles and A times a bigger volume and A times that energy, then the entropy also should be A times bigger. This is extensivity, right? Now, you see from here that if you compute this here, you get an A here, and I mean the A which comes from here cancels with the A which comes from here, but there is an A which arises here which does not cancel. So if you do the calculation properly, here you get A times S of N, V, and A plus 3N K over 2 times the Nk times log A. So there is an additional factor here, and actually, I mean, this is, I mean, if you rewrite this formula in the form where, so Nk log V plus 3N 2K log of 4 pi N E over NH squared 3 plus 1. Then you see that the problem really comes from this term here. So this term is clearly when you increase n and increase E, then E over n is an intensive quantity. Okay, is energy density. This instead depends on V. Okay, it does not depend on energy density. So this entropy is not extensive. And, we would like to understand where is the problem. And the problem can be understood if we think about an experiment, as Gibbs did. And the experiment is the following. So imagine that you take two gas, and these two gas, like in our example, are gas which we call A1 and A2. Let's imagine there are two different gases, okay, different species. And now here there is a number N1 of particles in a volume V1 and an energy E1, and here there is N2, V2, and E2. But now we assume that these two systems are in equilibrium. Okay, so they are in equilibrium in the sense that the temperature T1 is equal to the temperature T2. The temperature here is equal to the temperature here. And the energy density is also equal. Well, the pressure is also equal, which means that the density is also equal if they are two ideal gases. Okay. So these are two ideal gases which are in equilibrium. And now what you can do is to remove the wall between the two gases. What will happen? What will happen is that particles from this side will go into particles in this other part of the system, and particles here will go to particles on the other side. So the system will mix. Okay. And of course the entropy will increase. Okay, because now before the particles of system 1 were only in this part, and those of system 2 were only in this part, but now they will be completely mixed. And it's and you can also imagine that if you take a a configuration at random of the system, it will be very unlikely that you get all the particles of 1 in this side and all the particles of 2 in this side, okay? So typically you will get half, I mean, yes, you will get them well mixed. So this is really an irreversible transformation. You see a transformation when you take out the wall, you're really doing a transformation which is irreversible. And then there must be a change in entropy. Okay? So the entropy of the system must increase. Okay? If there is an irreversible transformation. Okay? So let us compute this change in the entropy. And so the change in the entropy is just can be computed by the fact that essentially the energy, these are ideal gases, okay? So the energy only depends on the temperature, so the energy is not going to change. So what is really, and the number of particles of the two systems is not going to change. So what is really going to change is the volume, okay? Each of the two systems is going from a situation where it occupies volume V1 to a situation where it occupies volume V1 plus V2, okay? So the change in the entropy is really, so the entropy of system, so what I only care about, so the entropy of the ideal gas, as we said, is n k times log v plus another part which depends only on n and e, but this part is not going to change, so I don't care about this, okay? So the change is that at the end I will get n1 particles with in volume V1 plus V2, n2 particles in volume V1 plus V2. This is the final entropy, and the initial entropy is n1 particles in volume V1 and n2 particles in volume V2. Okay? So, so this is just n1 k log V1 plus V2 divided by V1 plus n2k log 1 plus V2 divided by V2. Okay? Okay, now, so this is positive. Right? This is positive. This is the entropy, and this is called the entropy of mixing. Now, the point is, now imagine that the two gases are the same species. Now, if the two gases are the same species, then when I remove, and they are in equilibrium, when I remove the wall, the particles which were here will start moving here and etc. But at a certain point, I can think of putting the wall again. And I will have a thermodynamic system, a macroscopic system, which is in no way different from the one I started with. Okay? And, right?
But there is a wall that's kind of interaction.
I mean, these are ideal gases. Okay, so I'm just saying, I'm taking two ideal gases, And initially they are in this configuration, and there is a wall, and they have these densities. The density is equal, the pressure is equal. Then what I do is I remove the wall, and I put the wall again. So there is no experiment which I can do to say that the macroscopic state at the end is different from the macroscopic at the beginning. Okay. So the the change in the entropy must be zero, because this is a reversible transformation. I mean, there is nothing I have changed in the system, so it's a reversible transformation. So, but if I take this formula and compute the change of the entropy, then I would get this result. Anyhow, so there is a problem here. There's a problem, and this thing is called Gibbs paradox. And we'll discuss it next time. But as any paradox in physics is very useful because it teaches us something really fundamental. And so paradoxes are always very useful. Okay, so yeah.
Is this related with information?
Sorry?
The paradox, because we are analyzing one system in which we can distinguish particles.
Yes.
The next one we cannot.
Yes.
Identical.
Yes.
So it's kind of saying that the entropy, change of the entropy is related with the information that we have.
That is also, yes, that is also related to the information, it's related to the degree of disorder in the system, right? So, but also you can really, the two states before and after. I mean, if I do this experiment that I have two different species, I remove the wall and then I put the wall again, the two systems are really different, before and after. The macroscopic state is really different. I can do experiments which maybe detect, maybe particles of type 1 are, say, have some property which I can detect, or I have a different mass, for example. So I can see that some particles of mass. So I can do some experiments which detects this, and this is related to information. Okay, so there is some variable which I can measure, and from which I can say that the two states are different. Yeah. And in the second case, I mean, if they are mixing two identical things, there is no experiment I can do to. So if you want, there is no variable which I can associate to the system which will distinguish between the two states, the initial and final state. Right?
Because it's a really kind of, if we are relating a physical property,
Yeah.
the entropy, to the information that.
Yes, yes, yes. No, indeed, as you say, I mean, there is a prior information which I told you that on the type of particles. So I told you that the particles are different. Okay. If the particles are different, then this is an information. Okay. And the initial state and the final state will be very different. Okay. If instead the particles are not different, or you don't know that they are different, then you don't expect that the number of configurations should be different. Okay. Yeah. Okay. So see you on Friday.